Hello and welcome to this presentation on how to solve trigonometric equations. Alright, so solving trigonometric equations. So consider the following equation to solve. Example 1. Sine of theta is equal to 1/2. So to solve this, the solutions are going to be all the angle or angles theta such that sine of theta is equal to 1/2. So referring to the unit circle, that will show that there are two angles where the sine of theta happens to be 1/2. And these angles are going to be theta equal to pi over 6 and theta equal to 5 pi over 6. Now remember that the sine function is periodic with a period of 2 pi. So that means that there are infinitely many solutions of the format pi over theta equal to pi over 6 times 2n pi and theta equal to 5 pi over 6 plus 2n pi, where n is an integer. So what you will see is sometimes they're going to ask you for all the solutions, in which case you have to construct this base solution of the pi over 6 and then plus 2n pi, which is n times the period, and then this other base solution, theta equal to 5 pi over 6 plus 2n pi, 2 pi times n, the period times n. Now a lot of the times we're only going to be considering the solutions over the interval from 0 to 2 pi. In that case, we're looking at just the base solutions, pi over 6 and 5 pi over 6. So let's take a look at another example. This one's somewhat similar, but the difference causes a much greater jump in complications. So here I have cosine of 3 theta is equal to negative square root of 2 over 2. So just like before, this angle on the inside, which we're calling 3 theta, that the cosine of that angle has to be negative square root of 2 over 2. So if we look on our unit circle, every time where the cosine is negative square root of 2 over 2, there's going to be two places where that occurs. 3 pi over 4 and 5 pi over 4. So those are the two places where the cosine is going to equal negative square root of 2 over 2. Now, our angle was 3 times theta. So that means 3 times theta has to equal this 3 pi over 4, and 3 times theta has to equal this 5 pi over 4. We now have to solve each one of those angles, or each one of those equations, for theta. So for the first one here, where we have 3 theta is equal to 3 pi over 4, divide both sides by 3, that's going to give us 3 theta over 3 is equal to 3 pi over 4 divided by 3. Now if you remember, whenever you have a fraction divided by something, we've got to flip the bottom and change that to multiplication. So that 3 pi over 4 divided by 3, that's going to become 3 pi over 4 times a 1/3. And then when I multiply this, the 3 on the numerator and the 3 on the denominator will reduce, and that gives me theta equal to pi over 4. So there's one of our base solutions. For the other equation, we had 3 theta is equal to 5 pi over 4. So we have to solve this one the same way we did the other one. So we're going to divide both sides by 3. So 3 theta divided by 3 and 5 pi over 4 divided by 3. And just like with the other one, this dividing by 3, we're going to have to flip that and end up multiplying by a 1/3. So we get theta is equal to 5 pi over 4 times 1/3, which gives me theta equal to 5 pi over 12. So now we have the following two solutions. Theta is equal to pi over 4, and theta is equal to 5 pi over 12. Now if they wanted me to find all the solutions, infinitely many, I now have to add integer multiples of the period. Well, the cosine function normally has a period of 2 pi, but we have cosine of 3 theta, so this modifies our period. So to find the period of 3 theta, cosine of 3 theta, we take the normal period, which is 2 pi, and we divide it by that coefficient, 3. And so that gives me a new period of 2 pi over 3. So to find all the solutions to this equation, cosine of 3 theta is equal to negative square root of 2 over 2. We're going to have our two base solutions. The first one was pi over 4, so pi over 4 plus this new period, 2 pi over 3 times n, and that second base solution, 5 pi over 12, plus 2 pi over 3 times n. So this right here represents all of the solutions, all infinitely many. Now let's say we only want the solutions that go from the interval from 0 to 2 pi. So, to find which one of these are going to give us solutions from 0 to 2 pi, we're going to have to start plugging in values for n, like n equal to 0, n equal to 1, n equal to 2, and keep going until we have found all the values that are going to be between 0 and 2 pi. So, I'm going to start with this first one, the pi over 4 plus 2 pi over 3. Now, before I start plugging numbers in, since I'm going to have to do some arithmetic, I want to rewrite these using a common denominator. So I'm going to use the least common denominator of 12. In order to convert these fractions into over 12s, the first fraction I've got to multiply by 3 over 3. And the second fraction I've got to multiply top and bottom by a 4. So here we're doing this for the first fraction, multiplying top and bottom by 3. For the second fraction, multiplying top and bottom by 4. And this ends up giving me theta equal to 3 pi over 12 plus 8 pi over 12 times n. So now that I've got it written in this format, I'm going to start plugging in values for n to find all the solutions that this generates, and I want the ones that will be between 0 and 2 pi. Alright, well, for the other equation, modifying this one so that we get a nice common denominator, we're going to rewrite our fractions so the common denominator is 12. In order to do that, this second fraction has to be multiplied on top and bottom by a 4. And that's going to give me 5 pi over 12 plus 8 pi over 12 times n. And again, I'm going to do the same thing. I'm going to plug in values for n, 0, 1, 2, 3, until I find all the values this one generates that goes from 0 to 2 pi. Alright, so let's start with that first one that we had. 3 pi over 12 plus 8 pi over 12. When I plug in 0 for n, well, the 0 times this fraction, that goes away, and I get 3 pi over 12, which reduces to pi over 4. That was our original base solution for that particular part of the problem. Now let's plug in n equal to 1. When I plug in 1 for n, that's going to give me 3 pi over 12 plus 8 pi over 12, which gives me 11 pi over 12. So that's going to give me another solution. When I plug in n equal to 2, this gives me 3 pi over 12 plus 8 pi over 12 times 2, which gives me 3 pi over 12 plus 16 pi over 12. And when I add those, that gives me a 19 pi over 12. When I plug in n equal to 3, this gives me 3 pi over 12 plus 8 pi over 12 times 3, which gives me 3 pi over 12 plus 24 pi over 12. And when I add those together, that ends up giving me 27 pi over 12. And 27 divided by 12 is a number that is larger than 2. So this one is not going to be a solution inside of our interval. So we basically found 3 solutions from that first base solution. Now let's work with the other expression, the 5 pi over 12 plus 8 pi over 12 times n. When n is equal to 0, Plug 0 in, that gets rid of this fraction, that gives me 5 pi over 12. When I plug in 1 for n, this gives me 5 pi over 12 plus 8 pi over 12, which gives me 13 pi over 12. When I plug in 2 for n, that gives me 5 pi over 12 plus 8 pi over 12 times 2, which is 5 pi over 12 plus 16 pi over 12, which ends up giving me a 21 pi over 12. When I plug in 3 for n, that's going to give me 5 pi over 12 plus 8 pi over 12 times 3, which gives me 24 pi over 12 plus this 5 pi over 12, which is a 29 pi over 12. And the 29 over 12, that is larger than 2, so that one's not going to give me a solution inside the interval from 0 to 2 pi. So this equation, cosine of 3 theta is equal to negative square root of 2 over 2. That gives us a total of 6 solutions on the interval from 0 to 2 pi. We had our two base solutions of pi over 4 and 5 pi over 4, and then from those we were able to generate the others. So the pi over 4 generated 11 pi over 4 and 19 pi over 4. The 5 pi over 4 generated the 13 pi over 4 and the 21 pi over 4. So notice trigonometric equations are going to have multiple solutions. All of these solutions start with the base solutions that you would get from your unit circle, and then we add multiples of the period. Sometimes the period will be 2 pi, but if there's a coefficient, then the new period is going to be the old period divided by that coefficient. All right, let's take a look at another example. So let's consider this. Example 3, I have 2 sine theta minus 1 is equal to 0. For an equation like this, we have to isolate our trig function on one side. So adding 1 to both sides, that's going to give me 2 sine theta is equal to 1. Divide both sides by 2, I get 2 sine theta divided by 2 is equal to 1 over 2, and that ends up giving me sine theta is equal to 1/2. Now, in order to make these notes a little bit easier to deal with, I purposely chose this thing to simplify down to sine theta equal to 1/2 because that's a problem that we solved back in example 1. So we discovered that the solutions to this, sine of theta is equal to 1/2, the solutions to those are theta equal to pi over 6 plus 2n pi, and theta equal to 5 pi over 6 plus 2n pi. Now, if we wanted all the solutions, we would use these two expressions with the 2n pi's in it. But if we only wanted the solutions over the interval from 0 to 2 pi, that's going to be just pi over 6 and 5 pi over 6. That's what we're going to get if I plugged in 0 for n. If I plugged in 1 for n, then the values that it's going to calculate are going to be larger than 2 pi. So these are the only two solutions we get from 0 to 2 pi. All right, let's take a look at example 4. So example 4, I have cosecant theta is equal to 2. Now, I prefer working with the three trigonometric functions, sine, cosine, and tangent. One of the reasons why is because I understand those better. The other reason why is if for some reason I have to use my calculator because it's not a number from the unit circle, I have an inverse sine function, an inverse cosine function, and an inverse tangent function on my calculator. Alright, so let's convert cosecant to sine. So cosecant theta is the same thing as 1 over the sine of theta. So to simplify this, I'm going to multiply both sides by sine theta. So this ends up giving me 1 over sine theta times sine theta is equal to 2 times sine theta, which gives me 1 is equal to 2 sine theta. divide both sides by 2, and I get 1/2 is equal to 2 sine theta divided by 2. So I'm looking at trying to solve the equation sine of theta is equal to 1/2. And again, I repeated something that solved to the exact same expression. So the solutions of sine theta equal to 1/2, well, if you want all the solutions, it'll be pi over 6, that base solution, plus 2 pi n. And the reason why it's 2 pi is because the period of sine is 2 pi. And then we'd also have theta equal to 5 pi over 6, the base solution, and then plus the period 2 pi times n. Now, if we only wanted the solutions between 0 and 2 pi, then we just have those base solutions, pi over 6 and 5 pi over 6. Alright, for the last couple of examples in these notes, I'm only going to look at solutions that are on the interval from 0 to 2 pi. Alright, so here I have sine squared theta minus 1 is equal to 0. So I want to isolate this trig function. Add 1 to both sides, and that gives me sine squared theta is equal to 1. Well, to get rid of the exponent of 2, I'm going to take the square root of both sides. And notice this side that has the number, when I take the square root, I need positive and negative. So this is going to end up giving me two solutions. Sine of theta is equal to 1, and sine of theta is equal to negative 1. Well, when you take a look at your unit circle, there's only one place where sine of theta is equal to 1, and that's at pi over 2. And there's only one place where sine of theta is equal to negative 1, and that is 3 pi over 2. And since I said I'm only going to be looking at solutions now from 0 to 2 pi, so those are the only solutions from 0 to 2 pi. Alright, let's take a look at example number 6. This one also requires a little bit of algebra. So I have 2 sine squared theta is equal to sine theta. So I want to subtract sine theta from both sides. Doing that, that gives me 2 sine squared theta minus sine theta is equal to 0. Well, what I want to do now is I want to factor that common factor of sine theta from both of those terms. When we do that, that gives us sine theta times 2 sine theta minus 1 is equal to 0. So now we have to put each of those factors equal to 0. So I have sine theta is equal to 0, and 2 sine theta minus 1 is equal to 0. So let's solve this first one. Solving the equation sine theta is equal to 0, we need to find values on the unit circle that are going to make sine theta equal to 0. And there's two places where that's going to happen. Theta equal to 0 and theta equal to pi. I now need to solve this other equation. 2 sine theta minus 1 is equal to 0. Now this is the problem that we worked in example 3. So in example 3 we got the following two solutions. Theta is equal to pi over 6 and theta is equal to 5 pi over 6. So this equation that we started with, 2 sine squared theta is equal to sine theta, this would end up giving me a total of 4 solutions. And they are theta is equal to 0, theta is equal to pi, theta is equal to pi over 6, and theta is equal to 5 pi over 6. So thank you for watching this particular lesson, and I will see everybody next time.